Okay, it's working.
Okay. Okay. Hello, everyone. Welcome to today's Origin seminar. Today we have Andrea Guzmán Mesa from University of Bern. She's a last year PhD student, and so she's on the job marketing. She works with Kevin Heng and Christophe Mardassini on the intersection between exoplanet atmospheres, exoplanet interiors, and machine learning. She also has a math background, interested in science diplomacy, and talented in languages. Without further ado, let's welcome Andrea.
Thank you very much for the introduction, and thank you very much also for the invitation to join to the seminar. I wish I could be in Arizona at this moment, but hopefully we will meet with some of you in Las Vegas in the next few days. So I'm really excited about that. And yeah, so today I just want to share a bit of my recent work. I was able to, well, my paper was published last week, so I'm really excited about this. And for the past 3 years during my PhD, I have been focusing on a very interesting class of planets, which are the sub-Neptune planets, not only because they are the most common type of planet in our neighborhood, but also because they are predicted to be quite chemically diverse, or at least their atmospheres, as it is represented in this image that I like quite a lot. And I think that it encompasses really the spirit of my talk. So out of this class of exoplanets, one of my favorite that I've been also studying quite a lot is GJ426b. And GJ426b is a benchmark planet for atmospheric characterization. It was first discovered back in 2004 by Butler et al. Using the radial velocity technique. And later on in 2007, it was found transiting actually by Geelong et al., making this planet the first Neptune-sized exoplanet ever detected. And much of what we know about GJ426b atmosphere actually come from the Spitzer Space Telescope secondary eclipse observations by Stevenson et al. 2010. However, there has been a lot of speculation on what the atmospheric composition of this planet is based on these measurements. GJ426b is actually a planet that has an equilibrium temperature of 700 to 800 Kelvin, and at this equilibrium, or at this temperature regime, equilibrium chemistry predicts that its atmosphere is going to have high abundance of methane and a low abundance of CO and CO2. So let me show you this plot from Madhusudan and Ziegler 2011. Here, the red dotted lines show the 6 Spitzer band passes from 3.6 to 24 microns. The black lines, they show the extent of the absorption features here for different molecules like water, methane, CO, CO2. The gray curve shows a hypothetical model, a spectrum of GJ426b based on equilibrium chemistry, and the black circles are the integrated points in the Spitzer channels. So here I'm just going to focus on the first 2 channels, the 3.6 and the 4.5 microns. Here, the 3.6 micron channel is the key measurement in terms of constraining the methane abundance, and the 4.5 micron channel is the good one to constrain actually CO and CO2. And therefore, if we assume that that the atmosphere of GJ426b is in chemical equilibrium, the one that I just spoke about, a high abundance of CH4 and a low CO and CO2 would result in a deeper occultation at the 4.5 micron than at the 3.6 micron. However, this is not what is happening. So this is an emission spectrum from Stevenson et al. 2010, which I just told you, that measured the 6 photometric secondary eclipses in the 6 Spitzer channels. And here, the black square points are their observations. The red and the blue lines, they are different atmospheric models that have different mixing ratios for water, methane, CO, and CO2. And the color circles are the band passes integrated models. And then we can see that in contrast to the chemical equilibrium prediction, the occultation was actually way deeper at the 3.6 micron than the one at the 4.5 micron, suggesting that GJ426b atmosphere could be methane depleted. So what is going on? Later on, we have this paper from Bellew et al. 2011. Here they presented a simulated emission spectrum with methane being the predominant species. Here on my left, we can see the Stevenson data in crosses here for the different channels. And they found that the secondary eclipse data are consistent in this case with both a methane-dominated atmosphere as well with one that is methane depleted. If and only if the error bars for the first two channels are allowed to be larger, or to be much larger. They complement this emission spectra with the transmission spectra from the right. They use data from epoxy, HST, and of course Spitzer, and they found that the observation strongly suggests that the methane is the most abundant element in the GJ46B atmosphere. So now we have two sides of the story, one that says that actually the atmosphere could be methane depleted, and this one that says that is methane rich. But then in 2014, Notte et al. Reanalyzed independently the data from Stevenson, and they were able to corroborate the general finding that GJ46B atmospheres might be indeed methane poor. However, if there is something that is different in Notte's analysis from Stevenson, is the fact that for the 3.6 micron channel here, the occultation was significantly lower than the Stevenson's in emission. This is here a transmission spectra, and in blue and red are the chemical models from Stevenson, which they use, as I said, the low CH4 and a high CO2 mixing ratios. And the equilibrium chemistry model here in yellow, 50 times solar, is strongly disfavored by the Spitzer data because it just gives you the wrong planetary radius between these two channels. So the analysis from Notte also encourages the idea that we could have a methane poor atmosphere. So what is going on? Why can we just fit this 4.5 micron data point if the atmosphere is actually methane poor or depleted? Where is this methane? Or could there be a mistake with the observations, or is everyone simply wrong? What is going on? So I'm not the only person that have been asking this for my PhD, at least. There is a wealth of literature around it, but I think we could put it down to mainly two ideas. Maybe it's because there is something going on with chemical equilibrium or disequilibrium, or it could be maybe because the atmosphere could be a very high metallicity one. And I'm just going to show you some examples for these both hypotheses. This is a figure from Madhusudan and Seeger 2011, where they show observations on the model emission spectra for GJ46b. They also have here in the black circles the observations from Stevenson, and the green and the red curves here, they show two model spectra. The green one is based on non-equilibrium chemistry, while the red one is equilibrium 1. And we can see that here the best fit constraints on the chemical composition, they require substantial deviations from equilibrium chemistry with solar metallicity for this case. So a high metallicity is required for a high CO2 abundance in this paper. Moses et al. 2013 also tried to show different metallicity models compared with this Spitzer data, and the outcome of this paper is that there needs to be a high metallicity atmosphere to explain this finding too. And finally, this is a transmission spectra from Knudsen et al. 2014, which also seems to favor high metallicities. They actually show 3 models for comparison, including, again, the 2 models that we can find in Stevenson et al., but also a hydrogen poor atmosphere that is almost like 1,900 times solar. And they find that this metallicity, this very high metallicity, is consistent with the current constraints for GJ46b bulk composition. So I wanted to chime in this conundrum about this very exciting atmosphere. And for that, I am also inspired by a paper that I just showed you, Moses et al. 2013. I decided to investigate the atmospheric diversity of the sub-Neptune planets, and especially how atmospheric properties like metallicity, the carbon to oxygen ratio can influence the composition of the atmospheres or this class of planets. And actually, it's not very crazy to think that these atmospheres could have very high metallicity. This plot from Thorngren and Ferney, they show the expected mass dependence of the metallicity. And then here we can see that increasing the metallicity with decreasing mass. And here we have also for benchmark or for comparison, Saturn and Jupiter. We see that the regime for sub-Neptune planets are around this part of the plot. And so having something around like 100 or like 1,000 is actually not so crazy to think about. So let me show you for the first part of my paper, of my work. I came up with these chemical pie charts, as I called it, and they show the atmospheric composition of a standard sub-Neptune-like planet photosphere. In contrast to the work from Moses, I used self-consistent radiative transfer and equilibrium chemistry models rather than assuming just a physical, a fixed value for the temperature and the pressure as Moses did. And here in different colors on the right, we see the different constituents for these atmospheres. And so this is the equivalent plot also found in Moses et al., but I decided to explore a wider parameter space. So, well, here I have different, as I said, compositions of C2O and metallicity. And here we see that, for example, in the first row, with the C2O equals to 0.1, a very low one, due to the lack of carbon, the oxygen-bearing species actually start to dominate the composition as the metallicity increases beyond the 10 times solar. So for 10,000 times solar, we see that O2 here is the one that becomes dominant in equilibrium. And this also emphasizes the fact that oxygen or O2 by itself is not necessarily a good indicator of biological activity on exoplanets. On the other hand, we have here atmospheres with a carbon to oxygen ratio of unity, and we see that they are distinctly different. Here, basically, the carbon becomes locked in CO in orange and CH4 or methane here in red, and the oxygen is mostly bound in CO. So we see that at very high metallicity ratios, the atmosphere is dominated by carbon monoxide with only minor contributions of CH4 as a carbon carrier. And this is because CO is just a very chemical stable molecule. So it makes sense that most of the carbon and the oxygen atoms are locked in this molecule. So having studied these very high metallicities, it makes sense to ask ourselves, as Notte et al. 2014 pointed out as well, if they actually make sense, if they are actually consistent with the radius and bulk density of the planets. And this is an actual extract from the paper. It is not clear if such a high envelope metallicities, as I just showed you, are consistent with the radius and the bulk density of the planet. Also, Hu et al. 2013 was also encouraged by this fact, and they explore a Helium model to try to explain this. So not high metallicity, but a Helium model. So this takes me to the second part of my work, where I try to couple this knowledge that I just gained from the atmospheric composition of these atmospheres and trying to couple it with the interior structure of the planets, but I just focused here on GJ46b. So to that end, I used a bunch of codes, but just a couple of them to highlight. Helios, which is an atmospheric model, is a code written by a former student in my group, Mathieu Malik, who's now also in US doing a postdoc. So I used Helios to compute 9 atmospheric models for different C2O and different metallicity values. And using the outcome of it, like the pressure at the bottom of the atmosphere, the interior temperature, the total mass, I computed the interior structure for each one of the cases that I'm gonna show you soon. And so using this output, I use it here as an input in this completed 21, which is also a code written by my advisor, Christophe Morvazzini, who's an expert in planetary interiors and evolution. And basically, Completo, what it does is to solve the classical 1D spherically symmetric planetary interior structure equations. In our case, for the interior models, we assume a fully mixed hydrogen helium plus water layer instead of assuming either a pure water layer or a pure hydrogen helium envelope, and I think that's important. So using mainly these two codes, I came up with a grid. This is just like how the grid looks like for one of the outputs of the interior structure. So as I told you, I had different values for CTO and metallicity, but also here you can see that in gray, some squares, and it's because I obtained some non-convergent interior structures, and I'm gonna explain to you what this means in a second. So what does it mean to find a physical self-consistent solution when I try to couple the atmosphere and the interior of the planet? So the ones here in gray. What I mean with this is that for the assumed atmospheric composition that I get from Helios and the associated resulting temperature and the density at the bottom of the atmosphere, we were able to find an interior structure that also reproduces the bulk structure of the planet. This is the total mass and the radius. Here, this figure shows the envelope and the mean core density for a poor enriched case with a C2H of 10 times solar and a C2O of 0.5, which, well, this is a solution, a case where I actually found a solution. I use radius to the third power here just as a proxy to the volume. And in the plot, we also give the envelope gas density at the core envelope boundary here in dotted lines. So we can see that the observed mean, well, this is something that I should mention too. Here, this is the observed mean density of the planet from the observational data, which is around 1.76 grams per centimeter cube. And then now, for us to obtain this density, the total mass must be distributed in an appropriate way into the envelope of the planet, which has a lower density, and the core that has a higher density, such that the observed mean density here, they result, well, at least similar, that actually it's plausible. Here is another case for which we have also found a physically plausible atmosphere plus interior structure in green. This is a much more enriched case of 100 times solar at the same CO. And in this case, as it is expected, we have a higher density for a higher enrichment level. So this is an example where, we were able to find this physically consistent giant atmosphere interior model, actually for this green case. So let me just show you some of the parts that we were able to couple. Here, the parts modeled by the atmospheric and interior structure are shown in different color. For the atmospheric part, we found it in blue, and then for the interior, we found it in red. So in the top left panel, we show the pressure temperature profile. And we see that as we go actually deeper into the planet, the temperature actually increases as expected of around 14,000 Kelvin at the core envelope boundary. And for comparison, the temperature actually at the core envelope interface for Jupiter is like around 20,000 Kelvin. Also here we see the density versus, the density versus the radius. We see that it is continuous and it is monotonically decreasing with increasing distance from the planet's core, which is also expected. Another value that we were able to couple was the Rosland mean opacity as a function of the pressure. And the Rosland mean opacity by construction is continuous and actually increases as expected with the pressure and the temperature. And finally, here we have the enclosed mass as a function of the radius. And as expected from the density structure, we see that almost all of the planet's mass is contained in the interior of the planet, here in red, and with only a small fraction of it forming here in the atmosphere, this blue part that we see here. So I just presented you the nice results, but now what does it mean to be physically implausible? So let me show you this case with metallicity of more than 3,000 times solar and a very high carbon to oxygen ratio of around 1. And this case corresponds to a very dense gas. And as I said, we didn't find a solution. And this is because for such a very heavy element-dominated composition, the density in the atmosphere increases so fast that most of the planet volume is already filled with envelope material that has a density higher than the observed one. And given that this envelope of very high density, what the algorithm tries to do is that it tries to find the envelope mass fraction fitting the observed mean density. And then it does so by decreasing more and more the core mass fraction. But even, so what the code finds is that for a planet that only has an envelope, an atmosphere without any core, the gas itself is so dense relative to the observed value that no subconsistent coupled atmosphere interior solution exists. So here, this shouldn't be mistaken by an actual profile or a structure. This is just the last iteration before it stops, because it is just found that even for no core, the planet density is too high. So therefore, this extremely enriched atmospheric composition is inconsistent with the observed bulk density. So now I want to share with you some of the outputs also from this grid, both from the atmospheric models and from the interior models. So here, color-coded, I have the mean molecular mass. Just to see some trends, we find that, for example, if we fix a C2O value, if we increase the metallicity, it results in a linear increase of the molecular weight. We can also see that increasing the C2O ratio for a fixed metallicity value decrease the mean molecular weight. And this is just connected to the chemical composition of the atmosphere. At higher C2O values, the water disappears while the atmosphere starts to become more dominated by hydrogen itself. So this is consistent with our intuition. Here we also show the temperature at the bottom of the atmosphere, what we call BOA. The distribution of these temperatures, as in comparison to the other panels, it doesn't show like an overall trend. And this is just because the temperature depends strongly on the actual TP profile, which in turn also depends on the smaller trace gases such as methane that do not, so it is not like a linear process in that sense. But we can observe some overall global trends. And we see that with increasing metallicity, the temperature also increases, and this is just caused by higher abundances of strongly absorbing molecules as we go up. Now for the interior, and as I already mentioned, we assume that water is the representative of all the species different than helium, hydrogen. Therefore here Z, the water mass fraction, is a placeholder for all the heavy elements. And this one is obtained by requiring that the density obtained with the interior structures equations of the state is the same as the one in the atmospheric model. So we can see here that the observed behavior of Z is actually connected directly to the behavior of mu. Sorry. So we see here that a low metallicity leads to a low water mass fraction too. And this is just because in these cases, hydrogen and helium are dominating the interior, whereas here at a very high C2H, 2.5 in log, we have a metal-rich interior, and therefore the Z value are actually bigger. And I think the most important output for these interior structural values is the envelope mass fraction, actually. So here, color-coded again, we have the envelope mass fraction. And here we see that for a fixed CTO, as we increase the metallicity, the envelope mass fraction is also going to increase. And this is just because the chemistry is more and more dominated by heavier molecules such as CO or water rather than hydrogen or helium. And this means that the density of the envelope gas increases, which means that a less massive silicate iron core is needed to obtain the observed mean density. So just to say an example, for example, what does it mean, this envelope fraction of 0.95? It means that 95% is contained, well, the envelope mass is almost 95%, which means that only 5% of the total mass is in the silicate iron core. And this is just not possible, at least from a planet formation and evolution or disk chemistry point of view. So that makes sense that as we go up from this value, we also do not have converged structures. So what have I said so far? First, I confirmed the chemical diversity of the sub-Neptunes presented in Moses et al. 2013, but with the novelty that I used self-consistent atmospheric models. Second, I coupled the atmosphere to the interior in the case of DJ46b, as I show you. Something important too, of course, is that the atmospheric models for DJ46b are excluded, some of them by the interior structure. And something to keep in mind, which is going to be important by the end, is that we consider chemical equilibrium throughout all of these computations. So let's go back to DJ46b conundrum from the beginning. As I said, I wanted to contribute to this mystery. So to that end, and well, I tried to run an atmospheric retrieval to be able to constrain the planet's chemical composition in terms, again, of the CTO and the metallicity. And I used actually the random forest machine learning technique, which is incorporated into a code called HELA from one of my former PhD colleagues at Bern, Chloe Fisher. And I applied HELA to the Spitzer secondary eclipse observations. Here in this panel, I can show you the median fit that I got for DJ46b emission spectra. And similar to the other studies that are presented in the beginning, we see that our models also fail to fit the 4.5 micron Spitzer channel. And the main reason for this, we believe, is the underlying assumption of chemical equilibrium, which I adopted in the study. Here I see that the best posteriors that describe this median fit are actually this very high carbon to oxygen ratio and a very high metallicity as well. But actually these values are here in red. They are part of the non-converged values, and they are actually the same example that I show you for the physically implausible atmosphere interior structure. So we think then that the reason that this 4.5 micron feature does not fit is because most likely the atmosphere of DJ46b atmosphere could be in chemical disequilibrium. So it's not because of a high metallicity, as it is already excluded on the grams of the interior structure, but we really think that it could be because of this, and as it is outlined in Line et al. 2011, could be due to a mix of, like, for example, vertical mixing, photochemistry, among others. So, oh, that was quick, I ran. So just some take-home messages. I already said some of them, but I guess one of the important things, as I just said, is that probably this atmosphere could be in chemical disequilibrium, and this is something that I'm gonna keep exploring for the last paper of my PhD. And looking forward to JWST data, we also recommend that the analysis of the emission and transmission spectra, at least for this type of planets, are done self-consistently, both using our knowledge of the atmospheric and interior structures. So with this, I'll say thank you and take your questions.
Thank you, Andrea. If you have any questions, please raise your hand. So I'd like to ask one first. So in the planet interior density versus volume plot, you showed 2 or 3 models with different metallicity. I noticed they have quite different radius. So is the radius of planet a known value, or why do you have different volume?
Thank you for asking me this question. So they actually arrive to the same radius. It's just that I cut it here just to show it, because otherwise it just goes like way low in the density scale. But they do actually arrive to the same radius. They do not have different radius. Yeah.
Okay, so how do you determine the boundary between the envelope and the atmosphere?
That is given by the atmospheric model, actually.
Is it at a fixed pressure or at the optical depth?
Yes. So I do remember that I chose that one based on the contribution functions. So based on the contribution functions, I decided more or less which pressure and which temperature it made sense to make the cut out there. So yeah, this is just like an output, and we just like check what made sense in that part.
Okay. We have a question from Maxim in the chat. He asks, how is the boundary of atmosphere? I think is that my question?
Yeah, I think that's
okay.
You asked.
We have a question from Daniel.
And very nice talk. I had a question about, you mentioned James Webb. So I was wondering, in terms of constraints that we get from, or we hope to get from James Webb, which constraints do you think would be the most powerful for determining the internal composition and also the the composition basically. And sorry if I missed, if you covered this, I missed some of the talk because of
no, definitely not. So you're asking, what do I think that in terms of the data that we're gonna get is gonna be the most important to be able to constrain the interior structure?
Yes.
Well, I think this is why it's important to, basically, I think the transmission and the emission spectra that we get, right? And it's important that we keep trying to do this coupling between the interior and the structures, because everything we know about the interior must come from the atmosphere at least. So I do think that having good constraints from the emission and the transmission spectra must be good in terms of getting information about the interior. I don't do as much observations as I do theory, but I do think that it is going to become more relevant the more that we study or that we get more observational data to do this theoretical part and see what we can get. Yeah.
And do you have a specific molecule that you think would be particularly constrained here, C2 ratio or metallicity? Or what would be the most constraining, you know?
I do think I had this conversation with Christoph Mortassini, and probably just because of the way we lay out the study, probably water is the one that could make much more sense. And this is because of we also have a limitation of equations of the state for the interior, right? There are no known, what is the name? The equations of a state, they have to be tailored to the different molecules. And I think the most easy one, or the one that we use, is water, right? But probably, this one is going to be the most simple one, or the one that makes much more sense.
Okay, thank you.
Everett?
Sorry if I missed this as also. With these chemical disequilibrium grid that you're doing, is it going to have like a quench point, or are you going to have like free chemicals that don't assume anything about the chemistry?
Yeah, so we are gonna do the quenching point approximation, but this is something that I'm just gonna start actually like in 2 weeks when I incorporate back into my PhD. But this is the way we are gonna go, because I have tried to explore other ways of doing it, and they just become very complicated. And we think that going like, you know, maybe less complex is the way to go to explore this one. Yeah.
Okay, thank you.
Vladimir?
Yeah, my name is Vladimir Rapidin, and I have a question about the star itself. So, if it is the chemical disequilibrium, then the stellar activity can contribute to the formation of disequilibrium, specifically, you know, the dissociation of CO2 into CO. And if you don't have enough OH, then you can accumulate CO and run into the, you know, the runaway regime for CO. And also, you know, if you have, you know, energetic particles as a result of the stellar flares, then you can dissociate CH4 successfully, and the particles of the high energies all the way to a few giga-electronvolts can penetrate down to the few bars. So have you looked at the impact of the activity, and what do we know about the star itself?
Yeah, thank you for the question. This is a question that comes up very usually in the talks that I give. This is unfortunately not something that I take into account, but it's something that we definitely have in mind. But I agree with you that having this information from the star is important, is probably one that contributes to this either core power loss or core power mass loss or the photochemistry, etc. But yeah, this is something to keep in mind.
Yeah, given that the planet, the B planet is so close to the host star, right? It's like 0.028 AU, so that should be a very important factor. Thank you.
Yes, thank you.
Do you have any more questions? It's the last call for the questions.
I think someone was raising their hand.
Okay, I don't see any more questions. So let's everyone to thank Andrea again for the interesting talk.
Yeah, you can unmute and clap.
And see you everyone next week for the debate.